invitation to come and spend time here and to speak. And so I have to apologize right away that what I'm speaking on is somewhat far from the themes of all the other talks that I've heard so far and that are coming up. And so I will try to keep it a bit general as to what I'm talking about. There's a connection, it's dynamic, it's connected to combinatorial problems, but in a very different kind of vein than the other topics. So let me set the setting. It's A will be a finite alphabet. It will be any finite alphabet, but often I will say the size of A is 2 because my alphabet is 0 and 1, but that's just, I really mean any finite alphabet. And so you put the discrete topology on here, and then we'll look at the product topology on the sequences with entries in the finite alphabet, by infinite sequences with entries, and it's classical to put the shift on it, so that sigma will denote the left shift. Okay, so I mean sigma x at the ith entry. I'm not sure what notation to use, but it would be moved over one, shifting left. Okay, so what's a subshift? So I said I will start very general, just to. By a subshift, I just mean any subset, possibly equal, of A to the Z that's closed and invariant under this shift. Okay, so it's closed, shift invariant. And I will get to the other words in my title of complexity and periodicity in a moment, because those will be tools for understanding the shift. Actually, let me define what I mean, first of all, by the complexity of the shift. So this is Px, this is x of n, is the number of different ways to fill in a block, a consecutive n block. And so that's what I mean at the end. So the number of different cylinder sets, or an n block. Okay, so I mean looking at any x in little x in my x, and you place a consecutive block of length n, and I look at how I can fill it in with zeros and ones, or from my finite alphabet, how many different ways. So, and I'm, for here, when I write px of n, I mean consecutive n. The window is the size n. More generally, I could look at other finite patterns, px of f, and this may come up if we have time to talk about how this comes up for a more general finite cylinder. Okay. So this is the exponential growth of this is the topological entropy, but what I'm going to be interested in is things with zero entropy. So just to note the exponential growth rate. There's the topological entropy, but my interest here will be zero entropy. And let me back up a moment and say that everything I'm talking about here is joint work with Van Seer. And so if I neglect to mention it again, all the theorems are joint with him. Okay, so I'm interested in shift with zero entropy, and I want to study the automorphisms of the shift. So what do I mean by an automorphism? So I have a shift, x sigma, and that's my topological dynamical system. And an automorphism is a homeomorphism that commutes with the shift. Okay, so sigma phi is d sigma. So this has been studied since the 60s, and for the full shift, and by full shift, I just mean this is A to the Z with sigma. This was studied by Curtis, Hedlund, and Linden. And the results are described in a paper of Headland. There's no paper of Curtis, Headland, and Linden, but he describes these results and says they're due to himself and Curtis and Linden. And what he says is that the automorphism group, so by aught of whatever I write, I mean all of the automorphisms. The automorphism group is big. And in what sense is it big? Well, he says, well, it contains copies of lots of things. And for example, one of the results that they have in this paper is it contains isomorphic copies of any finite group. That's one example of objects that are contained in this automorphism group. Another one, he says, there's two involutions, and the product has infinite order. So the theme, at least, that I just want to take away, I mean, without going into the details of what this means, is that the automorphism group here is big, in some sense. And there are other results along these lines. There's a result of, let's see, I think it is Boyle, Linden, Rudolph from the 80s. This is a paper that was published in 1988. And they study a different class, and I won't give all the definitions because it's not relevant for what I'll say, but if you're a topological mixing subshift of finite type. Okay, so some big class. It includes, for example, the automorphisms, the full shift, subshift of finite type. And once again, they show it's big, the automorphism group. It contains the free group on two generators. It contains direct sum of countably many copies of Z. Okay, so I will just, again, the automorphism of this shift is big. It contains a direct sum of countable copies of any collection of finite groups. Okay, so just, you know, it's a large space. It is countable. It is countable, but okay, but it's actually even residually finite, but it's a big space. And
is the finite closure large?
Oh, I don't know. I don't know. But the theme that I want you to take away from these types of results is that the automorphism group is big, and what they use to do this is they actually construct these things in the automorphism group. They're explicit constructions that are not easy, but they're explicit constructions, and they use the fact that this complexity, px of n, it's positive entropy, has exponential growth, and that plays a fundamental role in these constructions. Okay, so what we became interested in, for reasons that I I hope become apparent by the end of the talk, was the opposite case. When can you say that the automorphism group is not big? When can you restrict it and say, you know, it's small? And what turns out we knew a lot of things about low complexity in our work, Van and I, and so we asked, well, what happens if you have a group, a subshift, with low complexity? And so let me state a theorem. And I'll say what everything means in 1 second, but first let me write down. If this is a topologically transitive shift, okay, and by transitive I mean that there is a point such that it generates everything so that sigma to the n of this point is equal to x, the orbit closure. Okay, so there is a point with dense orbit. Of subquadratic, and I will define that because it's not exactly, maybe it's the wrong word to use, but I will. Subquadratic growth, so it relates to this px of n and is somewhat quadratic in flavor, I'll tell you in a moment. And if H is the subgroup of the automorphism group of this shift, generated by the shift. Okay, so then it turns out if you look at the full automorphism group and mod out by this H, which is just generated by sigma and its powers, then the automorphism group of X mod H is a periodic group. So let me explain, put the theorem back so you can see it in a second, but what do I mean? So by periodic, I just mean every element is finite order. I don't mean that there's a maximum order for everything. Okay, so every element has finite order. And the other thing I need to tell you exactly what do I mean by subquadratic. Well, subquadratic if you look at the complexity function and you divide by quadratic, exactly the quadratic n squared, and I take the limit as n goes to infinity, okay, that this should be 0. So this puts a lot of restrictions on what the what the automorphism group can be. It's much more restrictive. Than the previous results that I told you about of Curtis, Hedlund, and Linden, and the later results of Boyle, Lind, and Rudolph. So in contrast to that, where we do not, obviously we have low complexity here, much lower. There's a lot of restrictions. Now, on the other hand, this includes a lot of well-studied shift systems. For example, it includes the class of Sturmian shifts. So a Sturmian shift, or it applies to, these are the class of shifts that come from coding of an irrational rotation, and they're the ones such that the complexity px of n is equal to n plus 1 for all n. So it's a linear complexity.
And is this locally finite? Is this group locally finite? Is any finitely generated subgroup of this finite, or
is any finite set of odd x mod h?
yes, or does it have a potential counterexample for bird-side thing?
I don't think so. I don't think so. I don't know. We've never looked at any of it. No, I don't think so.
You can give an example where it is not trivial.
So it's not trivial for Sturmians. I mean, the automorphism group, yeah. You mean why are there non-trivial automorphisms in it?
Would they come from like automorphism? Like you can make an associated graph to a Sturmian thing, right?
So for Sturmians, it's let's see. You want explicit examples of an automorphism? You can have involutions, not for Sturmians, but you can have involutions sometimes. Sturmians, there's no involutions besides, but for things where the growth is higher, like the complexity is 2n, then you can have involutions. So there's a lot of, it includes a lot of other examples. It includes other ones I think that may have been discussed, interval exchange transformations. Because here the complexity is it's on the order of magnitude of kn, where k is the number of intervals. I think it's actually k minus 1, n plus 1, where there's k intervals. It includes quasi-Sturmians, which are things where the complexity is not exactly n plus 1, but it's something like n plus a constant.
You can work out explicitly what it is.
Yes, Sturmian theory, you can do the full, you can write down, I'm just giving it as an example. It's not such a good one because you can explicitly say it's much better than the result that comes out of our theorem.
And it has been done? No,
it has been done, yeah. It was published, there's a recent paper by somebody named Olli who published the Sturmian and a few other examples of explicitly computing the automorphism group. OLLI. I think she was a student of Carl Peterson. So. So these ones, px of n is n plus c for some constant. There's other ones, I won't write them all down, but Roger, our new shifts you can do this for, purely morphic shifts, and this gets into actual quadratic growth rather than these ones, which are all linear type growth. But for example, as an example, if you take the substitution system, the Tuimors, that comes from 0 maps to 0, 1, and 1 maps to 1, 0. And I'm not going to talk more about this. I will, and for people who don't know what these are, it's okay. I'm going to move on. It's just in a bunch of examples for which it does apply. Okay. And let me give you one other theorem, is that because many of these are linear complexity or lower than quadratic, and so for those, with the same notation before, if you have a topological transitive subshift, so as above, I'll take in x sigma, topologically transitive, but now I'm going to ask that it has sub of linear growth. Okay, and linear growth, by this I mean that you have px of n divided by n, and this is a weaker condition. I just asked that the limit is finite. Okay. Then, once again, h is the same. H is above. And then you can look at the automorphism group of x mod h. And now it's not just a periodic group, but it actually has finite exponent. Okay, so all elements have finite order, and there is a maximum for the order here. So this includes some of these examples, the ones. So I want to say why, okay, so we have complexity here in this, and so far the part of the title which I haven't gotten to is periodicity. I haven't said anything about periodicity. And the motivation of this came actually out of some results from about periodicity. So let me,
So what does finite exponent mean?
so every element is a finite order and there's a maximum, a uniform maximum, yeah. Okay. So when we looked at these because with the following motivation, let me tell you sort of the short outline of the proof for both types of results. There's different technical issues that come up, but the outline basically is the same. So this is a one-dimensional problem, right? We're looking at shifts, bi-infinite sequences. These are Z. But what we do is we take the automorphisms, and instead of staying in one dimension, we produce a Z2 shift, a two-dimensional object. So we use the one-dimensional automorphisms to build two-dimensional call them configurations. So instead of being in a to the z, where we started, we're going to build things in a to the z squared, and then work in a to the z squared. Okay, so we build these colorings of z squared, same finite alphabet. So what do? Is if you start with some x in my shift space and an automorphism, I can build a two-dimensional object by taking the x and applying the automorphism to it. This is phi of x. And applying it again, this is phi squared of x. So schematically, I hope you see it going up the board and going down, apply phi inverse. Each one of these is a bi-infinite sequence. And together, looking at a shift, an element of the shift space, and all of the automorphisms produced by this one element, fixing a single automorphism phi, then I produce something in this space, a to the z squared. So I take a one-dimensional configuration and I produce a two-dimensional one, and I look at this as the natural inclusion in a to the z squared in the two-dimensional space. Okay, so this gives me a nice homeomorphism that here now I have two shifts. I have the left shift, the sigma that I started with, which I'll write as S. So S corresponds to sigma, the left shift, so Sx of I comma j is x at I plus 1 j. I hope I'm keeping the same notation that I had before. And I have another shift, which is the up and down shift now, or the moving in the other direction. So Tx of I j is x at I j plus 1. And the inclusion of this configuration inside here, and all of them, and I produce all of the configurations. So I get for each one, I start off with a, I guess maybe the way to write it is I start off with an x and a phi, and I produce some configuration, eta of phi and x at ij in a to the z squared. Okay, is the construction clear? Okay, so this gives me some collection of etas in a to the z squared, and the complexity assumptions that I started with, well, I erased the quadratic one, but the linear or the quadratic assumptions that I started with tell me something about the types of complexities that I can get out for these guys, these etas in z squared. Okay, so the one-dimensional, it gives me some kind of bounds, and then I have to use these bounds on a two-dimensional complexity, which I will have to define for you. Allow me to apply a theorem, which I will spend some of the time remaining describing, a theorem of Poisson-Zamboni, which I will state explicitly for you, and it'll take me about 10-15 minutes to get there. But what this theorem does is it allows me to say, given a complexity assumption, I get a periodic configuration L. And once I get some kind of periodic configurations out of this process of building them, I can deduce the one-dimensional results that we want from the two-dimensional things. So I need to really define for you, what do I mean by this two-dimensional complexity, and what type of results on the two-dimensional complexity can I apply for here to say things about the one-dimensional shifts. So the interest here is that I'm starting off with a one-dimensional problem, passing to a two-dimensional problem, using some techniques from two-dimensional symbolic dynamics, and then returning to the one-dimensional problem to solve it. Okay, so that's the outline that I want you to keep in mind, and now I will spend the rest of the time telling you what are the two-dimensional techniques and the issues there. Okay, so in order to tell you more about the two-dimensional problems, I'm going to go back to one dimension and tell you the classical results that relate periodicity, because that's ultimately what we need to get out from here, is a type of periodicity to get these finite exponent or the periods, and complexity. So this is a classical relation if I have a one-dimensional configuration. Now I'm not talking about the whole shift generated by it, I'm just talking about a single configuration eta in a to the z. Okay, so I can define what it means for this to be periodic. Eta is periodic. So this eta, I'll write it as eta of n. Okay, so it's n in z. If there exists some non-zero n such that, well, the obvious thing, eta of n plus n is eta of n for all n. Okay, so it means there's a window that I can copy and move, and I get the same thing over and over. Okay, so that's the same type of window as before. And the complexity, well, I've already defined it for the shift, but I can define it for a particular eta. So P sub eta of n is the number of configurations in an n block. Okay, if eta generates the entire, if you use eta to look at its orbit closure under the left shift, then I get exactly the same complexity that I defined before, px. So for transitive, these shifts, these are the same. In general, they may or may not be the same. So this complexity function, it's very easy to write down some basic properties and to use them to prove a classical relation, which I'll tell you in a moment. But what are the properties I'm going to need? Well, P8 of 1 is the size of my alphabet. Okay, if my alphabet is not used, just throw those letters out of my alphabet, and I don't care about them. For all n, P8 of n is a non-decreasing function. P8 of n is less than or equal to P8 of n plus 1. Okay, that's obvious. If I look at an n block and I increase it, I certainly saw all the previous configurations. These two facts are enough to prove a theorem of Morse and Hedlund from the 1940s, which says that if I have a bi-infinite eta, it's periodic if and only if there exists an n such that the complexity of the n window is less than or equal to n. Okay, so the proof is sufficiently simple that I'll give it to you on the remaining space on this board. Okay, so one direction is obvious. If you're periodic, use the period, and that's the right n to do this. So I'm assuming the other direction that there is some n such that the P8 of n is less than or equal to n. If my alphabet has one letter in it, we're done, because the only sequence is a constant, right? So P8 of 1 is bigger than or equal to 2, which is less than or equal to P8 of 2, which is less than or equal to P8 of n, which by assumption is less than or equal to n for some n. Right? There exists such an n, or an n0, let's say. So what does that mean? That means somewhere along in between it stabilized. P8 of I was equal to P8 of I plus 1. Okay, what does that mean? That means if I look at a window of size I, there's a unique way to complete it. Because there's only one way, either way, you can go left or right. And if you look at windows of size I, there's only at most 2 to the I of them, which means if I keep going, 2 of them repeat. Once I see one that repeats, I'm forced every which way to go, and so I'm periodic. Okay? Well, I said I'd write it on the board, but I don't have to write that. So this means, I'll just say this means unique completion. Of window of size I. Okay, and then by the pigeonhole principle, 2 of them repeat, and now you're finished. Okay, so that's one dimension. It's a nice equivalent. And then I want to put all this in 2 dimensions so that I can use these types of results. So, okay, the configurations will be an a to the z. Well, for now I could just say zd, or d bigger than or equal to 2, but the relevant one will be 2 dimensions for a variety of reasons. And the first thing I want to define is periodicity, and I already have choices by what do I mean for it being periodic. Because periodic could mean there's a direction in which I'm periodic, or it could mean there's a single configuration, like in the one-dimensional, that I can copy and do everywhere, i.e. all directions are periodic. Okay, so I will just say eta is periodic if there is a periodic direction. So if there exists an m that is not equal to all identically 0, so this is an m in zd, such that eta of m plus n is equal to eta of n for all n. So this is just one direction. Okay, so there can be d independent directions, and that would be fully periodic. Okay, so that's different than just periodic. In one dimension, it's the same thing. And now for complexity, I also have choices, but for the type of problem that we want, it'll be rectangular complexity that's interesting. So p eta, and I'm just going to write the 2-dimensional one. You can immediately see what the d-dimensional one would be. This is the number of configurations in an n by k rectangle. So you do the same thing. You take your n by k, fixed n by k, move it all over the configuration eta, wherever, and count all of the types of, all the different configurations that you see. And that's the complexity. Okay? I could, obviously this is P8 of n1 up to nd is the complexity of the d-dimensional parallelepiped. Again, you move it everywhere in eta. Okay? Now, the full periodicity here, the reason I'm ignoring it, or I will ignore it shortly, is that it doesn't give much information. It's much too strong a condition. If eta is fully periodic, so eta is fully periodic, if and only if P eta of N1 up to ND in this generalized parallelepiped type of complexity is actually bounded. Okay? And again, this is a very similar proof. You use the Morse-Hedlund theorem. So this direction is again obvious. If you're fully periodic, use the full period, and that gives you a bound on the number of configurations there. And in the other direction, well, if it's bounded for everything, it's bounded in particular, all the one-dimensional ones are bounded, right? So if I just forget what's happening in all coordinates other than the ith coordinate, then this is bounded by some m for every single one of these, right? Because it's bounded, so I just can look here. In this coordinate, use the Morse-Hedlund theorem, okay? Because it's bounded. In particular, there exists an n such that P eta of n is less than or equal to n. So in this coordinate, it's periodic. Okay, so if I take the period there and multiply by m factorial times d, that's a bound for the periods of the whole thing. Okay, so m factorial d is a period. Maybe much bigger than I need, but it's certainly a period.
I'm just confused. It's bounded or it's linear?
This one is bounded. This when it's fully periodic, it's really bounded.
But in Hedlund it was Pn less than n.
This is the existence of a single n such that P eta of n is less than or equal to n. Right?
This is a single point, right? Eta is a single.
Eta is one configuration.
It's an assertion about a single configuration.
Right. It's a single configuration. I'm not generating the system. But the complexity, if I take eta and I look at its orbit closure, I will only get things in the orbit closure whose complexity is less than or equal to etas. Right? Because you can only lose complexity in the orbit closure. You can't gain anything. So this will be relevant in a moment. But the point of this was just that full periodicity is really not going to tell us much about this. Okay, so there was a conjecture from the late 90s from Maurice Nivat, which said that in 2 dimensions, this is an analog of the Morse-Hedlund theorem. If there exist n and k such that, so eta is a configuration, you see this? And a is d squared. If there existed n and k such that the complexity of the n by k rectangle is bounded by its area, so it's less than or equal to nk, okay, then eta is periodic. Okay. So first of all, what this says is there is a direction of periodicity. It does not claim that it's doubly periodic. Okay, and you can pretty easily come up with examples that are not doubly periodic that satisfy this. Secondly, if k equals 1, this is just the Morse-Hedlund theorem, or the direction that requires a little bit of an argument, right? If k equals 1, you're talking about P eta of n1, the one-dimensional is less than or equal to n, and then you get periodicity. But it's not an equivalence. There are periodic guys which do not satisfy this in 2 dimensions. And the second very important thing is that it is a 2-dimensional conjecture. In 3 dimensions, b bigger than or equal to 3, the analog, you could want the analog of there exists n1, n2 up to nd, or let's say nk and l, such that p eta of nkl is less than or equal to the area, nkl. This is false. And this is an example in a paper of Sander and Teitman. And they have it in all dimensions, but just think in 3 dimensions, you can have 2 lines that are non-parallel and non-intersecting, so 2 skew lines. Code those by 1s and put 0s everywhere else. Obviously, this is not a periodic configuration, and it satisfies the kind of bound that you want. You can check. It's less than this bound. You have to do the checking. So this is really a 2-dimensional phenomenon. And there have been some partial results along these lines. So now I hope you see why we're getting closer to the result that I said I wanted, is something about two-dimensional configurations being periodic coming out. And that's exactly the type of thing in this conjecture, if we had this type of a complexity bound. Okay, so
Is there any kind of function of n and k's for ni's in higher dimensions?
okay, so there's none even that's conjectured at the moment. There's some examples of I'll tell you who in a moment when it comes to me, which are unpublished, which show that any kind of, but written, I mean, I have the paper, that show that no bound that you would hope, like a polynomial in this or something divide by some large number, you'll see there's no such result so far. And even if you assume minimality and some other kind of nice dynamical conditions, his examples work. Let me tell you who is. It's terrible. I can't remember. Yeah, I'm getting old. Can't remember names that I've said 100 times. Cassaigne, Julien Cassaigne. Yeah. So there are partial results along this. The first result in this direction was in this paper of Sander and Seidman, or another paper maybe of theirs, which said that if there exists n such that p eta of n2 is less than or equal to 2n, so the 2 by n configuration, then eta is periodic. Okay. So then there was a result of, so this is Sander and Teitman. Then there was a result of Epifanio, Koskas, and Vignosi, which said that if there exists n such that p eta of nk is less than or equal to nk over 144, then it's periodic. And then there's a result a few years later, this is around 2004. There's the result that I mentioned before of Kwas and Zamboni, and I'm going to need something slightly stronger, so I'll state that in a moment. But first, let me finish telling you these results. And theirs is if there exists n and k, I should put n and k, such that p eta of nk is less than or equal to nk over 16. Then eta is periodic. And then there's a result of Van and myself, which says that if there exists n and k such that p eta of nk is less than or equal to nk over 2, then you get periodic. Yeah, we haven't made it there. We still have over 2. And there's another result that we have is if there exists n, the three-dimensional guys, we also know how to do. If there exists an n such that the three-dimensional one is less than or equal to 3, and this is the full conjecture, then you get periodic. Okay. So what I said before is that we use not our theorem, which is ostensibly stronger, but we use this theorem of Kwas and Zamboni. So let me explain why we need their theorem and not our theorem, because a priori it doesn't look that way. In fact, if you go into their proof, they prove a bit more than just the fact that you have this complexity bound implying periodicity. They prove that you get, from this complexity bound, you don't just get periodicity, but that the periods have to come from a finite set. And it only depends on the choice of n and k and not on the eta. So the result is slightly stronger. So let me state it is if there exists n and k, so all the etas are in a to the z squared. I'm not writing that anymore, okay? If there exists n and k such that this is less than or equal to nk over 16, there exists a finite set, f, and the important part about this finite set, it doesn't include 0, otherwise it would be not very interesting. There's a finite set that depends not on eta, it only depends on n and k. Okay, so it's f of n comma k. So that the periodicity, which is in there, is eta of, I'll write it as x plus a vector is equal to eta of x for all x, where this vector v comes from that finite set. Okay, so it gives you in advance, if you have a bound of n and k, a bunch of periods that you can use. And that's exactly the right tool, which I don't think I will tell you how exactly this plays the right role, but I hope you could see the flavor, is that a result like this, where I get a finite bunch of choices, will give me the kind of period that I need in the group of the automorphisms in this construction. So I have to go back then from this construction, the two-dimensional one, and go back to the one-dimensional and see how this finite set plays this role to do this. And we use their theorem both in the quadratic case and in the linear case. Okay. So what I want to do, though, in the remaining about, I guess, 10 minutes, is tell you a little bit of the ingredients that come into these theorems on the complexity, that prove the periodicity in these cases. The arguments that we use are quite different than the previous arguments. These arguments are much more combinatorial. There's somewhat of a dynamical flavor in here as well, but our arguments are really translating this into a dynamical problem and using techniques of topological dynamics. So before I do that, any questions about the statement?
So you want to explain again how from this you deduce your...
It requires some work. You have to look at the block codings that come out from this and check that you get the right kind of control on the groups. But
once you have the periodicity, how do you conclude them?
Well, so once we have periodicity of this two-dimensional object, then we have to look at what that means, how that implies something about the one-dimensional that generated it. And that requires looking at the block codes that produce this. And so there's a little bit of work to do there. But I can show you later. It's not a hard argument, but I'd rather tell a little bit about these. Okay, so what's going on in these theorems is you're starting off with a particular eta, a fixed eta, and the first thing we do is make the obvious dynamical system that comes out from this by acting on it by the shifts. Okay, so it's two-dimensional, so you produce x eta, which is the orbit closure under TU. This will be a U in Z2. And this creates a nice subshift, two-dimensional object. It's closed and under translation. And what I pointed out earlier is that this system reflects the complexity properties of the original eta. If there was a complexity assumption here, then every x in this system also satisfies that same complexity assumption. It might be better, it might be lower. You might have a complexity drop, as you can see very easily by taking, for example, a configuration with a single one and all zeros elsewhere. In the orbit closure, you get all zeros. Okay, so there's a complexity drop, but it certainly can't increase. And the point is that as soon as I have properties of something that I can say about, well, if I see periodicity here, that reflects something here. Depends where the periodicity is, but if the whole system is periodic, that reflects what's happening in the original. So what we do is we study this system, and maybe I should say it, but you turn this into a compact metric space by putting some metric on here. So if you have alpha and beta in x eta, I just want a metric that says they're close if they agree a long time around the origin. So something like a metric, the distance is 2 to the minus, I don't know, minimum time that alpha of x is different than beta of x. Okay, so the first time they disagree, and so if they should be very close if they agree in a big ball around 0.
What is the minimum? Is in which distance?
It doesn't, all I care is any metric that says two guys, if they agree somewhere around 0, they should be close. Okay, so that's any metric you want. That will do. Okay, so there's a classic notion of what it means for a compact topological dynamical system to be expansive. So it's expansive if, let's just say x is my system, and I have a homeomorphism T. What does it mean for it to be expansive? It means that if I look at all the iterates, and two guys stay close under all the iterates, then they better be the same thing. So it's expansive if there exists some delta such that if you have 2 points, t to the n x, t to the n y, and they're less than or equal to delta for all iterates, for all n in V, then they better be the same point. So if you can see that they're going to stay together forever. So we need a notion of expansiveness restricted to lines for us, and this was introduced by Boyle and Lind in a paper in the late 90s. And I'm not going to give their full definition, but it's similar. You want to say that you have 2 things that are close, but you're only going to care about the iterates that are within some small distance to a particular line. But I'll just state it exactly for our case, and this is for the x etas that I'm talking about. So a line L, by this I mean like a regular line in R2, think about it as a line going through the origin maybe. If there exists some radius around it such that if you have 2 configurations and they agree, x and y, and they agree at all ends that are near this line, okay? So
this is a strip, it's not thinning, right?
it's a strip,
Okay.
that's right. So I want to say they agree around this line, and that's the little radius around it. So for all, I have to say for all n in the strip LR. Okay, so the strip LR will be all u, such as the distance between u and L is less than r. Okay, the line could be a rational line, irrational line, they don't.
Would you get, I mean, sorry, this is a very narrow question. Would you get a different notion if you instead took like only the points that sort of approximated the line really well if you took an irrational line?
Well, so this can be an irrational line, right? The line itself might have no integer points on it.
Ah, I see. Okay, so this is stronger. This is a weaker thing than saying I just want it.
That's right.
In a
Yeah, I'm not assuming that the line is rational. Okay, so a line is expansive. Oh, I didn't finish the definition. If there exists a radius so that when you agree in this, then they really are the same. X equals y everywhere. Okay, they agree for all n. Okay. So here, the reason I'm writing this here is I just said I want to pick a metric that just says 2 things are close. Okay, close means at least they have to agree in that spot. That would mean they're close. So this is, yeah, this is Boyle and Lind's definition in the most baby case. They give a much more general definition for ZD actions on a compact metric space. But and subspaces are expansive. And one of the theorems that they proved is that expansiveness, as you might guess, is not very common. I mean, just think about the full shift, right? You're not going to have anything expansive. Just because you know what's going on around the line, you can't tell me what's happening outside that line, right? 2 things might agree on an arbitrarily big ball and be different outside. And so what they prove is that as long as your compact metric space is infinite and you have a continuous action on it, then there's non-expansive lines. So non-expansive, and they prove much more generally that you get non-expansiveness of all dimensions below. Okay, here we're just working in 2 dimensions. And so non-expansiveness, you get lines. And so as a corollary of their theorem, so applied to x eta, and let me just be very careful that it's actually, this is just for 2 etas, dimension 2, that you conclude that this eta is doubly periodic. Okay, so in our context, what it says is that our x eta is infinite. Their theorem says there is at least 1 non-expansive line. And so what that translates to is that you're doubly periodic if and only if every one-dimensional subspace is expansive. Okay, and for that I mean with respect to the action by translations, the natural action by translations on the x eta space. And that's if and only if, and this is easy to see the double periodicity, if and only if the space is finite. So this is the first simple case. I mean, it turns out this is the easiest part of what we need to do. And there's no complexity bounds here. This is just a general statement that I haven't used anything about eta having some kind of Levat type assumption of existence of an n and k with certain properties. But what we show, and this is one of the main ingredients to the theorem at the top of the board, is that if you have, under this situation for x eta, and now I have a complexity assumption. And the first part we show is just if there exists an n and k, says that the complexity is less than or equal to nk. Not yet nk over 2. I'll say in a moment where that comes. Then you get, if you have a unique, so we always know that there is a non-expansive. This is from Boyle-Lynch theorem. And if there is a unique non-expansive one-dimensional guy, then it turns out that you're done, you're periodic, and you're not doubly periodic. The doubly periodic is hovered here. So if there is a unique non-expansive, so here it's one-dimensional, so I could just call it a line, then eta is periodic, and that means has a direction of periodicity. And to be very clear, it's not doubly periodic. Okay, because this course, if there was more than one, you would be in this situation, every subspace being non-expansive. Okay, and all the periods, it turns out, come from this unique direction. Okay, you get some line. And the second part of this theorem is, let's say in addition, you have this stronger complexity assumption of nk over 2. Okay, in addition to here, I'm assuming it's now stronger. Then it turns out we can prove that exactly this is what happens. There is at most one. There is at most one-dimensional, non-expansive line, I'll just write it as non-expansive line. Okay, so if you combine this part 2 with the fact that when there's a unique one, there is at most one, then you get exactly the periodicity that you wanted. But to prove that there is at most one, we need this stronger complexity assumption. We also prove this kind of a statement that there's at most one non-expansive line if you have the other assumption, which is the 3 by n case. Okay, so I think I've used up my time, so I'll stop.
Any questions? So if it grows, say, like cubic polynomials, so do you think it's still true? Or
So you mean the Anivat type conjecture or the automorphism
the
problem?
automorphism part?
So I think it probably still is, but we need a different result to do it. There is no analog of the Quast-Zamboni type theorem. You could assume and try to prove an asymptotic type result, that let's say you get something like subcubic behavior. This example of Cassandre rules that out too. But it turns out that I think we have another result that may become useful for the subcubic, and then you would get some results about the automorphism group for subcubic.
In the linear growth case, do you have example where this quotient group is infinite?
Where the quotient group is infinite?
Yes.
Yeah, where you can, to make it infinite is, there are examples, yes. We have not computed them, but I think there are examples, yeah. We just wanted to show that we're not too big. No. But these methods don't tell you what they are. They just tell you what they're not. All of our methods, right? It just rules things out. It doesn't explicitly construct anything. And it doesn't come out of our proof, any explicit construction.
So let's say Bryna again. And I would like to remind you that there is a pizza night today, so everybody is welcome. So it's 7:30. There will be some pizza and beer.
Mixing directions and so on. I just feel like the direction is not the right one for you.
So in this, the out of non-expansive, so the goal is to get single non-expansive. You pull out irrational is very important. And so then all you're down to is, I didn't have time to talk about that, but all you're down to is rational ones.
Yeah, but
Really,
okay, so you have this
Because
matrix.
I mean, I feel like that's maybe a more natural set, like satisfying Dirichlet's theorem.
So some kind of closer approximation.
Yeah, and then I think so you want that to separate points. That's a much stronger condition.
That's stronger.
Than this, right? Because you have way fewer points to separate them. Here you have sort of lots and lots of points that'll separate it,
Right.
and you barely have infinitely many that separate.
Right.
No, it might be,
It's probably, maybe.
it might be the same, because here, you know, when you're gonna get down to a single way that counts, you know, if the conjecture is correct.
Right.
This is actually because of the conjecture, it's not.
And I guess if you say for yours you can rule out irrational ones,
We
then it's
realize
fine.
irrational through the
Then-
class.
yeah.
Because what happens is you start off